Thank you, Gregory, and thanks to the organizers for inviting me to speak here. Can you hear me well? Okay. So I'm going to talk about activity-driven transport in harmonic chains. I'll explain what I mean by that. And this talk is based on the works, these works, first of which is already published, and the other one we are still working on. So this is the outline of my talk. So I'll just give a very brief recap of energy transport in thermally driven harmonic chain. And then I'll explain what I mean by active reservoirs and activity-driven transport. And in particular, I'll discuss the behavior of average energy current and temperature profile, and if time permits, also fluctuations in these quantities. And then I'll just conclude with some general remarks. Okay, so when we talk about transport, we usually have in mind a picture that a macroscopic system is connected to a temperature gradient, let's say for heat transport, and heat is flowing through the system. And we try to understand the behavior of this transport phenomenon. So as a theoretical model, it's often, as a simple theoretical model, in particular for 1D systems, it's often useful to consider the system as an oscillator chain, which are connected to some through some springs, or harmonic or anharmonic, and then the boundary oscillators are connected to thermal reservoirs, and these reservoirs are usually considered in equilibrium, so that the connection to the system must satisfy fluctuation dissipation theorem. And the relevant questions are: what happens to the energy current? How does it change if we change the thermal gradient? Is there a Fourier law? Can one define a local temperature? And what are the local velocity fluctuations or current fluctuations? So the paradigmatic example in 1D at least is the harmonic chain connected to Langevin baths, which was first studied by Ryder, Leboeuf, and Lieb in 1967. So I'll explain the model in a little bit of details. So we have here a chain of harmonic oscillators, so identical mass particles, which are connected to nearest neighbors by a harmonic spring of stiffness, let's say K. So here is my K. And it's also attached to fixed walls. And then the boundary oscillators are connected to two thermal reservoirs at temperatures T1 and Tn. Okay, so these reservoirs exert forces on the boundary oscillators. And these are typically modeled through a dissipation and noise. So here, the Xi1 and Xin are my noises, thermal noises, just white noises. And the fluctuation dissipation theorem means that the dissipation is related to the strength of the thermal noise. Okay, so, of course, there are many other possible models of reservoirs, but this is the simplest one, and we'll just stick to that. And this has been exactly solved in 1967, as I said, and it was shown that the current flowing through the system, it survives even in the large macroscopic limit, and the current is proportional to the temperature gradient. Okay, and it was also shown that the kinetic temperature, which is defined to the average energy of the oscillators in the bulk, that attains a uniform profile, and which is given by just the average of the temperatures of the two reservoirs. Now, the question that I'm trying to ask here is what happens when these reservoirs itself are away from equilibrium. So they don't have to satisfy fluctuation dissipation theorem. And in particular, the question I'm asking is what happens if these reservoirs are active? So, yeah, what I mean by active reservoirs, there were already some talks, particularly by Omar in last week, where he talked about the behavior of active reservoirs. So what I mean here is simply a collection of self-propelled active particles, each of which can consume energy from the environment at an individual level. And as a result, they're inherently non-equilibrium in nature. So motion of single probe particles in such active reservoirs is being studied a lot, as you also heard in Omar's talk. And this actually gives rise to certain intriguing features like emergence of memory and modification of equipartition theorem and negative friction, etc. So here the question I'm asking is on the next level, let's say. So we have two active reservoirs and a system which is connecting these two reservoirs. And what we are trying to see is how does the transport property of this system changes when we consider this system. I mean, instead of thermal reservoirs, if we consider active reservoirs, what happens then? And I'm going to take a very simple linear model. I will actually not consider the complications Omar mentioned. I'll just take the like 0th order approximation in the sense that the active reservoirs will be modeled by just an extra force acting on the boundary reservoirs, boundary oscillators. Okay, I'll not take into consideration what happens to the dissipation. So just to reiterate, so we again have a chain of harmonic oscillators connected to two thermal reservoirs, two different temperatures T1 and Tn, and constant dissipation, which I take to be equal for the two reservoirs, just gamma. And the action of the active component of the reservoirs are modeled through two additional forces which are acting on the boundary oscillators. So on the left oscillator, the first one, the force is F1. And on the rightmost oscillator, on the nth particle, there is another extra force, Fn. Okay? These I call active forces. And clearly now I have a violation of fluctuation dissipation theorem because these forces are extra. This component was already satisfying FDT. So what are these forces? So for simplicity, what I take is that these forces are some dynamical forces which have an exponentially decaying correlation. So the time scale of this correlation, that I call tau, that is my measure of activity. Yes. So this is, I mean, when you model thermal reservoirs, you also assume that the forces are being act on only the boundary reservoirs, right? You add these terms on boundary in addition to the thermal reservoir. Yeah. So I have an active component of the reservoir. And that, for simplicity, I'm taking that's just a single force. So it's the 0th order approximation that Omar was mentioning that, I mean, to start with, it was thought that active particles in a passive bath are similar, passive particles in an active bath are similar to active particles in a passive bath. So that's the model I'm using. So this is like an active force. So I'll show it what this is. So this will be basically like the dichotomous noise or ABP noise. So for the moment, these are just some forces, dynamical forces, which have a memory. Okay, so which have this. Yes, yes, yes. It does. I'll show it just in a moment. Yeah. So of course, I mean there could be many different dynamical processes which give rise to this kind of exponential correlation. But for the moment, I'm just saying that okay, some force which have this exponential correlation, and this. So at the two ends, we have these two forces, F1 and Fn. And correspondingly, there are two time scales, tau1 and tau n, which are my activity measures. So these are the reservoir activities, just characterized through one number. And when this activity goes to 0, at that limit, we expect some sort of a thermal behavior. I'll again come to that point. Okay, so as I was mentioning that there could be various different dynamics which give rise to similar exponential correlation, although their dynamical nature could be very, very different other than this two-point correlation. So for example, the simplest thing one can think of is just a run-on-tumble process. So this active force is just a two-step process. So the sigma is plus minus 1. It flips with some rate, alpha j. Okay. So this, I mean, so the force can take only two values with some amplitude aj, and that of course gives rise to this same form of correlation with tau j as 1/2 times the rate of flipping. So that's my, for run-on-tumble process, that will be my activity, measure of activity of the boundary reservoirs. On the other hand, one can also consider an active Brownian process where the force is of the form cos theta j, where theta undergoes a Brownian motion. There, the tau is given by the inverse of the diffusion coefficient of this orientation angle. These are rather abstract, but these are some processes which are already well known in active literature. So I am just, bringing them together in the same format. All of them have this exponential decay, although their dynamics are very different. For example, if we look at the actual propagator, those are very different in these cases. For RTP, ABP, we know. I mean, for RTP, it's simple enough. For ABP, the exact expression for all times is not even known. Then there is also, of course, AOUP, which is completely Gaussian. For that case, one can actually calculate everything. So this I keep just as examples. For the first part of my talk, I will not even need this specific dynamics, but if time permits, I'll come back to it. Okay, so the question that we are asking is, how is this non-equilibrium stationary state different from the thermally driven case? How is it different than the RLL model where we just had Gaussian noise driving the system. In particular, how is average energy current different? What is the behavior of the temperature profile and fluctuations of these quantities? Okay. So it turns out that because of the linearity of the system, one can actually calculate everything exactly using the same method Abhishek introduced in maybe about 20 years ago, just using a matrix method. So in the stationary state, one can write the displacement of the Lth particle from its equilibrium position in this form, where this G is a matrix. I will not go into the details of the calculation, but just to give you a brief idea of how we proceed, it's exactly in the same manner as in the original RLL model, although the results are very different. And they're different because of this spectrum which comes. So the spectrum of the active noise, which is actually Lorentzian. So for thermal noise, we just have a flat spectrum. It doesn't depend on the frequency. In this case, we have this noise correlation in the frequency space, which is a Lorentzian. So it has a certain width given by the activity of the reservoir, yes. And we expect to see the signature of this memory in the current and other quantities also. So what we calculate first is the average energy current, okay? And we know that in the stationary state, if we calculate, we'll see that in the stationary state, there is one constant current flowing through the system. And that we can calculate by taking the average energy flowing from Lth oscillator to L plus 1th oscillator just by taking the force times velocity, or even easier, just by looking at the average of the force on the boundary oscillator from the reservoir times its velocity, just the instantaneous current. So that's the energy flowing through the system per unit time. This is same for all oscillators because the bulk is completely Hamiltonian. So there is no dissipation or source in the bulk. And once we do this computation, it becomes clear that this current actually has two clear different components. One is the thermal component, which is exactly same as the RLL case. So it's just proportional to T1 minus Tn. And then there is an active component, which comes from the active forces. So because this is exactly same, I will not bother about it from now on. We'll just assume that T1 is equal to Tn. The thermal part, the temperature is the same. So this current is exactly 0. So we'll just focus on this quantity. So it turns out that this current actually shows certain intriguing features. So here is a plot of the current as a function of the left reservoir activity, tau1, while we keep the other, the tau n fixed for different values of tau n. And so the symbols are simulations with RTP dynamics actually. Although, the result will not depend on what specific dynamics we take. But here is a plot showing this. So we see, first of all, that the current is non-monotonic. So as we change the activity of one reservoir, keeping the activity of the other reservoir fixed, meaning that we are changing the strength of the drive, the current first increases and then decreases. So this is what is called negative differential conductivity, which is, kind of counterintuitive, but it has been seen in non-equilibrium systems. I will come to it in a moment. And another thing is that you see that the current also reverses direction. So at a certain value of tau1 star, it reverses direction, which is not equal to tau n. So these red points are those non-trivial current reversal points. Okay, of course, at tau1 equal to tau n, we expect a current reversal. But when, this is another value where the current seems to reverse the direction. So these two are, we haven't seen them in the thermal driven case. And particularly keeping in mind that this system is completely linear. Okay, so these are kind of intriguing features which come from the activity driven chain. So let's first talk about the negative differential conductivity. So what I mean by negative differential conductivity is probably already clear that there's a non-monotonicity. So if we take the local slope becomes negative. Okay? So yeah, so this dj act, d tau j is negative in certain parameter regime. So as I was saying, it's kind of counterintuitive, but it has been seen in certain non-equilibrium systems, as early as 1984 by Mustansir and Deepak. And there have been other examples, all of which are nonlinear systems. Otherwise, also if you have presence of obstacles or some kind of kinetic constants, then you can see this kind of behavior. But activity drive actually seems to lead to NDC even in this linear system. Yes, yes. Well, no, it's not time. I mean, it's a time scale, but that's the activity measure, right? So that is the parameter which is characterizing the reservoir. And if we change, why? I mean, you can do that. You can do that. I mean, but this is also driving the system, right? The activity difference is what is driving the system. The other thing also, you can generate probably a current keeping the activity same, but changing the amplitude. But keeping the amplitude same and changing the activity also generates a current. That is one kind of drive. Okay, I mean, yeah, you can call it something else. But on the other hand, when this there is a limit, the passive limit, where this tau exactly plays the role of temperature. That I'll come back to. Okay. Yeah.
Technical question. If you take the limit of overdamped oscillators, essentially m going to 0, the equilibrium result essentially came up to the curve of correction, so it's proportional to the temperature. What will happen with this?
This I don't know. We haven't done it yet. I don't know the answer, but we can check. I don't know the answer. But that probably can be checked easily. So yeah, let's stick to the underdamped situation still. So to understand, I mean, this NDC in a sort of hand-waving physical, from a physical point of view, what we can do is we can look at the spectra of the system and the reservoir. So remember that this is the form of the active current. Okay, I haven't shown the calculations, but it can be written in a form. So this is the transmission coefficient of the system, and that overlaps with the reservoir spectra. Okay, so if we plot this overlap, so this orange curve, that is the reservoir spectrum. It's a Lorentzian. On the other hand, the system spectrum has two peaks near its characteristic frequency, which is set by the strength of, stiffness of the oscillators and the mass of the oscillators. So if we plot this overlap between these two functions, we see that this overlap actually changes non-monotonically. So here for tau equal to 0.1, this blue curve, and that increases when we go to tau equal to 0.5, and then it decreases again when we go to even higher value of tau. So that's what is giving rise to this non-monotonicity in the current. So we have two components, two contributions from the two reservoirs. We are keeping one tau fixed, and this other quantity is changing non-monotonically, which is giving rise to the non-monotonic behavior. In fact, this is also what is giving rise to the current reversal. So just to remind you again, so as we saw from this plot, that the current changes direction twice. Once when the reservoir activities are equal, so that's this line. So this is tau 1, tau 2 plane, and this shows where the current is positive or negative. Okay, so as we cross this tau 1 equal to tau n line, of course the current will change sign. And then there is another curve, this solid red curve, which is basically tracing the path of this red dot here, okay, for a given value of k, m, etc. And if we change tau 1, keeping tau n, if we change tau 1, keeping tau n fixed, so we are following this red line, and we see that the current is negative first, then positive, and then negative, which is what we see here. So what is happening is that, so the two reservoirs are competing, okay, and if we keep one reservoir activity fixed, depending on which one wins, that decides the direction of the current. Okay, so I'll just pause here for a moment. Is it clear? So these are the two features we are seeing, both of which are related to the fact that the reservoir both of which are related to the fact that the reservoir spectrum is actually not flat, but it's a Lorentzian. Okay, and so there is also a subtle point. If you pass through that, then you don't, the current direction is not changed. Next, I'll come to the question of temperature profile. Gregory, how much? Yeah. Number of oscillators. Yeah. So these are all done in the n going to infinity limit. But as you can see, n going to infinity, here the simulation was done with 64 oscillators. So that's already large enough. Two, I don't know, but I mean from 10 onwards, yes. 2, one can actually calculate exactly. So yeah, for 2, I don't know, but I would expect yes. Okay, yeah. Yes. Now coming to the question of temperature profile. So for thermally driven oscillator systems, it's often customary to define a kinetic temperature from the average kinetic energy of the oscillators. For harmonic cases, one can also define a potential temperature just by taking the average potential energy of the oscillators. So here also we can do the same. And what we find is actually in the thermodynamic limit, these two temperatures, first of all, both of them reach a profile which is flat in the bulk, although boundary layers are different. But both of them also reach the same flat value. So kinetic temperature and potential temperature, they are identical in this n going to infinity limit. Okay, and in fact, if we look at the expression, this is given by this. So the bulk temperature is half of some quantity, which I am calling curly tau. So curly T1 plus Tn. This is exactly in the same form of the equilibrium, I mean thermally driven case, where of course this curly T1 and T1 were just the temperatures, but here it's something different which depends on tau and other parameters. Okay, so Rob, coming back to your question in a moment, so you see that this, if we call this some sort of effective temperature, this tau appears directly here. So that also, of course, raises the question that can I replace these active reservoirs, this active force, just by this number, calling it an effective temperature, okay, because it's in the same form as equilibrium. Yes. So otherwise, you will, of course, have an overall shift, okay, because it's linear, it just adds up. Right. But the answer to that question turns out to be no. We cannot simply call it an effective temperature. So there are certain differences. First of all, we have a non-trivial boundary layer. So look at this curve, this orange curve. This is for tau1 equal to tau n. Okay, so there's a flat profile, but that, I mean, we still have a boundary layer, which does not appear in the thermally driven case. So in the thermally driven case, if you have T1 equal to Tn, the temperature profile is completely flat. There is no boundary layer, nothing. Okay, that's one difference. Another thing is that there is no, I mean, these kinks which appear because of the contact resistance near the boundary for thermally driven case, they are completely absent here. Moreover, what we also checked is that suppose I assume that this is my effective temperature, I can calculate the current which would have flown through the system if it were a thermal reservoir, but that do not match. So here the dashed lines are those currents, assuming that those are the temperatures, and the solid lines are actual current flowing through the system. But what we notice is that if, so this is tau n equal to 0.1, which is small activity limit, and here if tau1 is also small, these two curves actually merge. So this is my passive limit. In this limit, we actually expect some sort of an effective thermal behavior. It can also be understood from simply by looking at the force correlation. So we had an exponentially decaying correlation of the force. And in this limit, in the limit tau going to 0, this can be effectively replaced by a white noise. And the strength comes out to be aj squared tau j. So you see, I mean, both A and tau together play the role of temperature in this thermal limit. So this is the effective temperature. And in fact, if we do the calculations and take the proper limit, it turns out that in this limit, one can write the current simply in the RLL form, which is proportional to the difference of the effective temperatures. Okay, so okay, here I'll just give a brief two-third way summary. So what we have been looking at is the energy transport of harmonic chain, which are connected to active reservoirs, and these reservoirs are modeled by very simple, just one parameter quantity, just some activity, tau1 and tau n. And they exert exponentially correlated force on the boundary oscillators. And we could calculate the average current flowing through the system exactly, and it shows negative differential conductivity and current reversal, which are not seen in the case when reservoirs are satisfying FDT. Okay, and also in this whole part, I have never mentioned what kind of dynamics ft goes through. I have just assumed that it's exponentially correlated. So the next question is, how do we distinguish between different sorts of active forces? Whether it's RTP or ABP or AUP, how do we distinguish that? So naively, one would expect that if we go to higher order fluctuations, so instead of average energy current, if we look at energy current fluctuations or velocity fluctuations, then we might be able to see signatures of the specific dynamics of active force. So this is what we started to do, and to our surprise, we found that actually, so if we look at the velocity fluctuations of the oscillators, let's say in the bulk, they turn out to be Gaussian, all of them. So here I have different kinds of active drive, AOUP, RTP, and ABP. AOUP, of course, is completely Gaussian, so we expect the whole measure to be Gaussian, but RTP and ABP are not. And to our surprise, it turned out that the bulk velocity distributions are Gaussian in all cases. So by looking at velocity, at least the typical fluctuations, we haven't seen the large deviations or anything, but the typical fluctuations are quite, described quite well by Gaussians. On the other hand, if we move towards the boundary, then we start to see some deviations. So here, this green curve is the velocity distribution of the first oscillator when the active force is RTP. Then we start to see that these are really different. But so far we have not been able to find any quantity which actually distinguishes between these different forces in the bulk. For example, we also measured and calculated the fluctuation of the local energy current. So far we have been talking about this, the average of this quantity, but now I'm trying to talk about the velocity, the current distribution, the full distribution of this instantaneous current. Okay, so because we saw that the bulk velocity distribution is Gaussian, so we also assume that let's see what happens if we take the measure to be Gaussian. So P XLVL, we assume that the whole thing is Gaussian in the bulk, and we calculated the distribution of this quantity. There's no reason why it should be, but we did the calculation, and then one can calculate this distribution exactly. It is of this form. And here you see that these black lines are this distribution, this Bessel function. And open symbols are the current distribution measured from RTP-driven chains, and the field symbols are from ABP-driven chains. So once again, they actually match. Match quite well. So this is again an evidence that somehow the system, maybe from the Hamiltonian nature, maybe from the linearity, the measure in the bulk seems to be Gaussian. Okay, and irrespective of what particular noise that we are driving it with. And this current distribution has also some intriguing features. It has a logarithmic divergence near the origin, and it has an exponential decay, which we would calculate. And here again, you see this the set of AVP and RTP curves, and these match very close to the origin also. So there is no deviation at all for small current. Yes, and then we come to the question of the current fluctuation at the boundary. So we also measured the distribution of this quantity for these different drives. Here we could not calculate exactly for RTP and ABP, but here again we see some really big difference between the three cases. So AOUP, of course, is Gaussian. We can calculate exactly. This has again log divergence near the origin. For RTP and ABP, the boundary current seems to have a finite bound, which comes from the discrete from the bounded nature of the force itself. So the bound we can also calculate exactly. But this nature is very different. The shape of the distribution curves are completely different in these three cases. So I will conclude. So what we have been, Gregory, how am I doing? Oh, okay. So I can take questions. So we have been looking at non-equilibrium stationary states of harmonic chain, which are driven by active noises. Active noises I'm modeling with simply exponentially correlated noise. Okay, very simple, just 0th order model. And already this simple model shows certain features which are rather intriguing. We have seen negative differential conductivity as a function of active gradient of activity, and also current reversal, which are again very non-equilibrium phenomena. And we also see that the behavior of the system is quite independent of at least the bulk behavior is quite independent of the dynamics of the force. Doesn't matter how we model this active force, as long as it's exponentially correlated, the local velocity and current fluctuations are consistent with a Gaussian measure in the bulk. So this is, again, a little bit surprising to us. And as you would expect, because boundary forces are very different, behavior of boundary oscillators strongly depends on the specific dynamics. But this also goes down very fast if we go just to the second or third oscillators. It's already, again, consistent with the Gaussian one. Of course, there are many open questions. The first question is, yes? The first question is how robust are these results? For example, if I take a more realistic model of the reservoir, so if I don't take constant dissipation, let's say, and make it consistent with what Omar was saying, that, I mean, the passive particle in active bath also has some corrections to the dissipation. If we include those effects, does it survive? That's, of course, the first important question. And what happens if we add disorders in the system or anharmonicity? So preliminary simulations seem to suggest that even if we take anharmonic oscillator chains, this negative differential conductivity and current reversal actually do survive, at least for finite length chains. And yeah, so that's it. So we still have a lot of questions which we have to look at. So thank you for your attention.